So what we're doing is we're going through and normalizing these continuity, the momentum equations, the energy equation. We're normalizing those or non-dimensionalizing them so that we can apply solutions to general situations. So we aren't constrained to one geometry, one set of temperatures, and so on. We can develop relationships that are more broadly applicable. So we went through these different equations. Here's the example of the energy equation. We took our dimensional energy equation at the top and converted it into a non-dimensional energy equation here. But in doing so, we have these dimensionless terms that come out of it. And where do these come from? Well, we didn't show the work on this particular one, but what we're showing here is that if I took, let's say, this term and I non-dimensionalize it, coming out of that term, you're going to have some dimensional stuff that's multiplying the front here. So then the non-dimensionalization happens when we divide through by the stuff that's multiplying those terms. So we divide through by things like rho cu infinity, right? And that stuff ends up giving you this whole mess here, which itself is a non-dimensional term. So simplifying that down, that gave us this stuff here, right? Reynolds number shows up, Prandtl number shows up. So these dimensionless terms, things that we then go on to describe these equations in terms of, those just fall out of dividing through to get dimensionless groups. What I want to do, just as a recap, is we're now getting into this, the correlations part. And so the correlations are always in terms of these dimensionless parameter sets. I want to remind us of what we have gotten so far, because we've kind of glossed over these a little bit. But just to get this all in one place, so the pink stuff and orange stuff I've added to this since last time. Let's just talk through it. So Reynolds number, remember, Reynolds number is the ratio of inertial forces in a flow to viscous forces in that flow. So if you have a very high velocity flow, you're going to get a lot of inertia, and that's going to, say, overwhelm the viscous forces and become unstable. That's where you get turbulence from. So that ratio is captured as rho times u times characteristic length over viscosity. The Prandtl number is a ratio of viscous diffusion to thermal diffusion. Remember, this is nu, our kinematic viscosity, over alpha, which is our thermal diffusivity. So that's the ratio there. That's a property property only parameter. There's a characteristic of the properties of the fluid. So Reynolds, Prandtl, you're really going to see those a lot in correlations. The Peclet number, we just briefly introduced. The Peclet number is simply the product of these two non-dimensional parameters here, so Reynolds times Prandtl. When you multiply them together, what you actually get is up here you have this kind of momentum or inertial thing. Multiplying it by the Prandtl number gives you, in the numerator, advective transport. So that is sort of how much energy am I moving by moving mass through some control volume. So advective transport, and then the denominator here is energy transport by conduction. So if I want to know how important is energy movement by bulk movement of mass to energy movement by conduction in a fluid, that is the Peclet number. The last one we talked about is the Eckert number. Briefly, again, we just, at the very end, talked about this. This is the ratio of kinetic energy of the fluid to energy diffusion across the boundary layer. So this one actually, unlike some of the other ones, includes temperatures directly as part of it. So the Eckert number is useful in helping you decide whether or not viscous dissipation is an important part of your solution. To do that, the Eckert number by itself is not good enough. You actually have to take Eckert over Reynolds. So if Eckert over Reynolds is a small number, then viscous dissipation is important. And viscous dissipation, remember, was, we go back here, viscous dissipation was this term here. So if Eckert over Reynolds is small, that goes away. Okay, so that's our recap. Hopefully we're up to speed now and we can kind of keep going with this. So what we'll do today is two things, hopefully. One is finish up our discussion of correlations, and then we'll get into the integral methods that you can use to actually develop models of boundary layers. What we're going to do is let's start with an example. The goal of this discussion is to get from these dimensionless equations to expressions that we can derive empirically, take measurements as you're doing in the homework, and relate it somehow to these dimensionless groups. The challenge, or I guess the really important part here, is figuring out which dimensionless groups are important for a given correlation. So we can do that by looking at these dimensionless equations and then kind of just seeing where there's functional relationships. So let's start with looking at, I guess, these top two up here. So these top two equations are continuity and x momentum. Those, if I solve those two equations together, that gives me information about the momentum boundary layer. It doesn't, nothing about the energy part of it yet, but the momentum boundary layer part of it. So those two are kind of a separate thing, or a group, and then the third one is kind of its own thing, separate from those two. So just starting with those two, let's look at what these are kind of telling us. So I have maybe two, let's say two independent quantities that I'm trying to predict from those two equations. Those two equations have x and y, they have Reynolds number, they have pressure gradient, but what they're really telling me is the velocity, the non-dimensional velocities that are involved in my system of equations, u and v. So I would use these to say, I'm going to come up with an equation for u, and I'm going to come up with an equation for v. If I do that, what do I know? Well, I'm going to say u is a function. I'm just going to say u is some function u. Weird notation there, but it's a functional relationship between what? So what is affecting u here? I would need to know the x position, x tilde, the y position, y tilde. What else would I need to know in order to compute u? I guess I would need to know dp dx. I would need to know Reynolds number. And I think that's it, right? So let's say Reynolds number with respect to L, and then dp dx. I guess this is written as dp infinity dx. So if I know those things, I can compute u. Also, same type of deal with v. So it's going to be x tilde, y tilde, Reynolds, L, dp infinity dx. So if I know those things, I can compute my u and v velocities using these equations. One thing actually I didn't say before, but maybe you should just make clear, we were writing the equations in terms of dp dx, and somehow this p infinity slipped in there. So where did that come from? Well, it's actually kind of a simple thing when you think about it. If we've made the assumption that y momentum is unimportant, that tells us that dp dy is unimportant. That means we're saying that there's really no pressure gradient in the y direction across a boundary layer. So if that's true, like if I picked some x position here and looked at the pressure difference between the surface and the boundary layer edge, it would be negligible. So if that's the case, then what that's saying is the only thing that can cause pressure to change as a function of x is a change in p infinity. So we've just kind of noted that by saying dp infinity dx, but it's actually important because p infinity is something that's outside of the boundary layer. So it's outside of anything that we're trying to solve for. That means for our purposes, inside the boundary layer, it becomes an input to our problem. It's like a parameter that we don't deal with directly. It's just something that is given to us to solve. All right. So OK, we have u and v relationships here. Let's use an example to kind of understand how this is going to work. So let's say we want to predict something we actually care about, which is like for a momentum would be shear stress. So remember our shear stress equation is tau s is equal to mu partial u with respect to y, evaluated at y equals 0. So to use this, I need to get that equation into dimensionless form, tau s equation. So I'm going to take, let's see, I'm going to take u and make that dimensionless. So that'll be tau s is equal to mu times partial of dimensionless u, which is u infinity times, or sorry, u tilde times u infinity, with respect to y, which is y tilde times L, and then evaluate that at y tilde is equal to 0. So doing that and then rearranging a little, we have mu times u infinity over L, those are all constants, times partial of u tilde with respect to y, evaluated at y tilde equals 0. So we're trying to get to this to a point where we can then have functional relationships with it and understand like where our correlation would come from. So let's express the shear stress in terms of its dimensionless form, which is the friction coefficient. So come over here. So this is friction coefficient is equal to 2 tau s over rho u infinity squared. So now if I combine these things, plug in that expression for tau s there, I end up with Cf is equal to 2 over rho u infinity squared times mu u infinity over L times partial u tilde with respect to y at y tilde equals 0. Just substituting that stuff in, and then simplify that further, and that becomes 2 over Reynolds number with respect to L, partial u, partial y, evaluated at y tilde equals 0. Okay. So what did we just do? Right? We're trying to come up with a relationship, a functional dependence for shear stress. So we're combining what we know about the definition of shear stress with the non-dimensional form to get to an expression for friction factor, or sorry, coefficient of friction with respect to non-dimensional quantities. So this here would be what we would need to evaluate to get our friction factor. So the outcome here is to say, well, if I'm going to develop a correlation, CF, I want that correlation to be, or my correlation is going to need to be a function of what? Well, it needs to be a function of u and y, maybe, and Reynolds number. So what is u a function of? U is a function of x, y, Reynolds number dp dx. But we are also noting that we're evaluating this at y equals 0. So if we evaluate something at y equals 0, then it's no longer a function of y. Right? So it turns out that the expression here is going to need to be a function of x, of Reynolds number, and of dp infinity dx. Okay? So again, this is saying if I'm going to develop a correlation, my correlation has to be in terms of these things. For a given problem, let's say, we remember that dp infinity dx is something that needs to be given to us. We can furthermore make the assumption that my correlation just needs to be in terms of x and Reynolds number, right? We'll leave it as this for now. Any questions on this methodology so far? So it's a little bit like, it seems a little hand wavy or kind of arbitrary, but just think about, keep the goal in mind. The goal is we're trying to figure out what our correlation needs to account for. This analysis tells us what it needs to account for.